All right, this is going to be section 2.5, and we're going to talk about continuity. And we're going to use the notes from that section. So the first thing that we're going to talk about is continuity at a point. So here's the continuity test that we're going to be using. You can see it in your notes. A function f of x is going to be continuous at a point x is equal to c. So c is just going to be the point, the x value, if and only if it meets these three conditions. And it has to meet all three of these. So the first thing is that f of c has to exist. So the function has to be defined at c. The second thing is that the limit as x approaches c of that function f of x has to exist. And the third thing is that the limit as x approaches c of that function has to be the same value as the value of the function at c, as f of c. And then also for one-sided continuity and continuity at an endpoint of an interval, the limits in parts 2 and 3 of the test, they should be replaced by the appropriate one-sided limit. So it works for one-sided limits as well. So then by definition, if f is discontinuous at a point c, it's discontinuous at a point c if it's not continuous at c. So it seems kind of obvious, right? So how can a function fail to be continuous at a point c? So let's go through those three criteria that it needs to meet and then look and see what it looks like if it doesn't happen. So the first one says that f of c is not defined, so that's a way that it can be discontinuous. So suppose that we have a graph, and let's put c here, and let's say that our function looks like this, and then we have an open circle at c, and then it continues there. So here f of c is not defined because the value of f at c doesn't exist. So it fails that criteria. The second one says that the limit of f of x has to exist. So it's going to be discontinuous if the limit from the left is not equal to the limit from the right. So let's draw an example of that. So again, let's say that c is here, and suppose our function goes like this, and here this time it's going to be defined at c, but then let's put an open circle here and continue it that way. And you can see that the limit as x approaches c from the left-hand side, the limit as x approaches c from the left-hand side is going to be whatever this value is here, and the limit as x approaches c from the right-hand side is going to be whatever the y value is here. So they're clearly not equal to each other. The last way that a function can be discontinuous is if the limit as x approaches c of that function is not equal to the value of that function at c. So again, let's draw that one. So let's say we have c here, and let's put an open circle at c. So what we have so far is that the limit does exist, and then if I put a closed circle here, it's defined at c, but the problem now is that the limit exists, it's defined at c, but those two values are not equal to each other. The limit would be the y value here, and the function would be defined here, so it doesn't exist. So another way that we can think about this is by saying that f is going to be continuous at every number in an interval if there are no breaks. So essentially you can think about it as being able to trace that function without lifting your pencil. All right, so that's continuity at a point, and then we're going to talk about continuity of a function. So a function is going to be continuous if it's continuous at every point in its domain, and we just talked about continuity at a point. So for a function, we're looking at every point in the domain. So a function is going to be discontinuous if it's discontinuous at one or more points of its domain. So here's some examples of basic continuous functions. So these are some functions that you know what they look like when they're graphed. So for example, sine of x, we can easily see that this sine function is going to be continuous because the sine function just oscillates between -1 and 1. The domain is all real numbers, so that function is definitely going to be continuous. Same thing for the cosine function. Cosine function is also going to be continuous because it's going to also go between -1 and 1. So that's definitely going to be continuous. And e to the x, it's going to be a continuous function. And ln of x is also going to be continuous. So basic functions that we already know that are continuous. And here's another example. So for this function f of x is equal to x minus 1 over x plus 1, for which values of x is this function going to be continuous? So this is a rational function. So the problem with rational functions come in the denominator, because the denominator can't be equal to 0. So these rational functions are going to be continuous everywhere. There's a polynomial in the numerator, polynomial in the denominator. They're going to be continuous everywhere except when that denominator is 0. So this is going to be continuous for all values of x. Except when that denominator is equal to 0. So it's going to be continuous everywhere except when x is equal to -1. All right, let's look at a couple more functions here and see if we can determine if they're going to be continuous. So first function is piecewise defined function. So it's composed of two parts. The first part is that rational function, t cubed minus 27 over t minus 3. And then the second part is going to be f of t is equal to 27 when t is equal to 3. So the problem, again, is going to come with that denominator. We have to be careful of that denominator not being equal to 0. So any potential problems are going to occur when t is equal to 3 here. So that's the thing that we have to look out for. So we're going to find out, we're going to do the three tests. So the first one that we have to find out is, we want to know, is f of 3 defined? Because that's the only potential problem, is at 3. So is f of 3 defined? So when t is equal to 3, is the function defined? And we can see that it is going to be defined, because here we see that when t is 3, oops, let me erase that. We see that when t is equal to 3, the value of the function is 27. So f of 3 is equal to 27. So yes, that passes the first test. All right, second test, we have to find out if the limit as t goes to 3 of f of t exists. All right. So that limit as t goes to 3 has to exist according to our according to the continuity test that we had up above. So let's check that limit. So we have the limit as t goes to 3 of t cubed minus 27 divided by t minus 3. And it's a rational function, and what we always want to do, we want to try to do, is plug that 3 in and see what happens. So when we plug a 3 into this denominator, that denominator is going to 0, so that's going to be a problem. Also, the numerator goes to 0 when you plug in the 3, so that's a problem. Then what we want to try to do is maybe some algebra to try and simplify this, or some factoring to see if we can find out the limit that way. So let's try and factor this, since the numerator is a difference of two things that are being cubed. It's a difference of 2 cubes. So we'll keep that denominator as t minus 3. And in the numerator, we're going to factor out a t minus 3, because t is being cubed and 3 is being cubed in that difference. So we have t minus 3. And factoring that difference of 2 cubes, we have t squared plus 3t plus 9. And then we can cancel those t minus 3's, and then we can try and plug that 3 into that rational function that's left. So when we do that, we get 3 squared plus 3 times 3 plus 9. So that's going to be equal to 9 plus 9 plus 9. So that's going to be equal to 27. And this is just asking us if that limit exists. And that limit does exist when t is equal to 3. So this part of the test is going to be yes. And then we have a third part of the test in our continuity test. And that is asking us, is the limit as t goes to 3 of that function f of t, is that equal to the same value that we got for f of 3? And it is, because we saw previously that f of 3 was equal to 27, and then we found out that that limit is also equal to 27. So both of them are 27, so this is yes. So this function is going to be continuous. All right, then I gave you the next function here is the next one. F of t is equal to t squared minus 9 when t is less than or equal to 3, and 9 minus t when t is greater than 3. Is that function continuous? So you can see that now 3, again, is going to be the number that we want to be looking at. And we want to look and see what's happening to the left of 3 and to the right of 3. So go ahead and try this one. Do the same thing here. Work through those 3 tests and figure out if this one is going to be continuous or not. All right, so I just started this one and we can finish this one together. So the first thing that we want to check for this function is we want to find out if f of 3 is defined, because 3 is going to be the only point that's going to be a potential problem in this function. So f of 3 is equal to 3 squared minus 9, because we're looking at this first function right here. And that's going to be equal to 0. So yes, f of 3 is defined. It's equal to 0. The second part of the continuity test, we have to find out if that limit as t goes to 0 of that function f of t exists. So we need to see what's happening to the left and to the right of the function, making sure that they're equal to each other. So first of all, let's check what's happening to the left. So the limit as t approaches 3 from the left of f of t is equal to the limit as t approaches 3 from the left of 9 minus t. Well, that's from the, well, that's not the right function. So let me fix that function. So from the left, we need to use this function here. So I wrote the wrong one here. All right, so let's write this function, t squared minus 9. And then what is that going to be equal to? That's going to be equal to 0 when we plug that 3 in. So that's 3 squared minus 9, and that's equal to 0. All right, so that's fine so far, but we also have to see what's happening from the right. So the limit as t approaches 3 from the right of that function f of t is equal to the limit as t approaches 3 from the right. And now since we're approaching from the right, we're going to use the second function here, 9 minus t. And then when we plug 3 into this function, we get 9 minus 3, and that's equal to 6. So we can say that, therefore, the limit as t approaches 0 of f of t does not exist, because the left-hand limit is not equal to the right-hand limit. So therefore, since it doesn't pass that second test, the function is not continuous. So f of t is not continuous. So if we were to graph that function and trace the function with a pencil, we wouldn't be able to trace that function without lifting our pencil up. All right. And then the third thing we're going to talk about in this section is continuous extension at a point. So when a function is not continuous at a point C, it's sometimes going to be possible to extend the domain of f to include x is equal to c, creating a new function that is continuous at that point C. So for example, if we have the function f of x is equal to sine of x over x, it's going to be continuous every point except, looking at that denominator, every point except for when that denominator is equal to 0. So we can extend the function's domain to include that point 0 so that the function is continuous at this point. So the way that we can write that is with this piecewise defined function. So we're going to write a new function, and we're going to call that capital F of x. And the first part is going to be sine of x over x as long as, and we can say we're going to use this as long as x is not equal to 0, because 0 is where the problem is in this function. And then we can define it to be something when x is equal to 0. So let's define that to be equal to 1. So if we were going to graph this, so at 0 we're saying the function is equal to 1. And then for the rest of the sine function, if we were just going to graph the first part, it's not going to be defined at 0, so we would have an open circle. But then the continuous extension, we're going to define it to be 1 at 0, so then we can fill in that open circle and make it a continuous function. All right, so let's look at another example. So let's define g of 3 in a way that extends g of x is equal to x squared minus 9 over x minus 3 to be continuous at x is equal to 3. All right, so g of 3, let's see if I can move this down here. So g of 3 is not defined because we're looking at this denominator, and we can see that this function isn't defined at 3. So little g of 3 is not defined. But let's see what happens when x is 3. So and now we're going to call this give it a different name. We'll call it capital G of x. And we're going to start with the original function x squared minus 9 over x minus 3. And now let's factor that numerator, x minus 3 times x plus 3. Divide that by x minus 3. And cancel those x minus 3's. And so now we're changing that function. And the new function, that capital G of x, is going to be equal to x plus 3. So these two functions, lowercase g of x and uppercase g of x, those are two different functions. They're actually the same function, except this one is going to be defined at 3, and this one is not going to be defined at 3. So this new function so big G of x is equal to x plus 3 is the same as little g of x except at x is equal to 3. So we say that big G of x is a continuous extension and it's now going to be defined at 3 because big G of 3 is equal to 3 plus 3, which is 6. All right, so that's how we're going to define that continuous extension. And that's it for this section.